Okay, Lewis structure with numerous structures you could have put. 2 DUS and 28 valence electrons, is that right? Just a couple of structures I put. Look pretty good. Bromine, carbon, hydrogen. So I have 2 DUS, 28 valence electrons, all standard bonding. There's no charges, standard bonding. Here I put a pi bond and a ring, my 2 DUS, standard bonding. Again, a variety of others you could have put. How we doing? Can you put together a structure from a few different elements? Yeah? Ketone and ester. Those look right?
Yeah.
Yay?
Sounds good.
Degrees of saturation 12, shortest bond C. How does that look? Yep. Lone pairs 10, yep.
10
10.
How we do?
on the sulfur?
Yeah, the sulfur.
I thought it was.
I thought it was only.
Yeah.
How we do?
Oh,
No? Questions? I think there's 9 pi bonds and 3 rings. Is that right? 9 pi bonds? I see 3 rings. Hopefully there's 9 pi bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9. Lone pair A is in a p orbital. This lone pair is in a p orbital because there's p orbitals next door. And then the lone pair B is in an sp2 hybrid. Graph those to help you get that. How we do?
Well, we did well until the last.
Did what?
Was doing good until you showed me the last one.
Question?
On the ketone, why is that not a phenol?
Ketone, why is it not a
Phenol, phenol, whatever. It's oxygen.
It's an OH. It's an OH.
oh wait.
Oh, you're right.
a phenol is an OH on an aromatic ring. It's not an aromatic ring. And it's not an OH.
All right, I was just looking at the ring part.
Not all rings are aromatic.
Okay.
But I forgot about this. Formal charges.
I looked into what an aromatic ring is. Okay, the key will be posted upstairs later on 3rd floor as you start walking down towards our lab. There's a glass case on the left as you enter the hall down to our lab. That's where the keys will be posted. Okay, physical properties, and we'll be hitting acid-base chemistry, acid-base handout, acid-base warm-up. Any questions about lab? This week we will begin a 2-week lab identifying an unknown, 2 unknowns. You'll be given a solid unknown and a liquid unknown, and your job will be to identify them. There are lists of the unknowns for you to choose from, to choose your answer from. You will be using IR. In terms of using IRs, we probably should divide, there's 3 different IRs, and we should probably almost assign you an IR to use. So if you start looking at directions, everybody's not looking at the same directions. Okay, we'll talk more about that on Wednesday, maybe dividing you into thirds with which IR to use. But any questions right now? Questions about anything related to lab?
What do you want your final report to do with you? You want tentative or type?
Let's say work process. And type. But make sure you read the directions.
Yeah.
Other questions? Okay, let's look at physical properties. There's a couple of miscellaneous pages in the back. Please look at those. I'm not going to refer to them now, but the miscellaneous is where we can apply our knowledge, see some examples. But any questions about the physical properties handout? Okay, let's look at the acid-base handout. I showed both of you this sort of intro in the lab. For example, these are the types of questions you need to be able to answer after we go through the material. Down the line there. Give you a preview. It's a very standard acid-base reaction over here. Okay? Very straightforward. You need to be able to show such reaction products for test one. The acid-base mechanism. Okay, I believe we looked at this in lab. Every acid-base reaction you do, you should follow the acid-base mechanism to predict what's going on and show products. Okay? Did we look at that in lab? Yeah? Acid-base chemistry. Okay, we can begin here. All right, this is just a review of your Chem acid-base chemistry, ionization of an acid to give the proton plus the remainder of the molecule, which is going to be minus. Okay, A is just the remainder of the molecule. It can be one atom or it can be a huge old multi-atom structure. Ka equals this. Of course, stronger acids will have a higher Ka. But we don't use Kas in organic chemistry. We use pKas. Stronger acid will have a lower pKa, right? Nothing here is really new. Of course, any acid, you must have a base. Here I'm showing water as a base, and here's your good old acid-base mechanism. Lone pair, these electrons. These electrons may bond to H. These electrons move on to A as a lone pair. And so now the oxygen has made an additional bond to H. Lo and behold, there's now a positive charge here. And the lone pair, bonding pair moves on to A as a lone pair. If A is neutral, it's going to be minus here. But this should really be nothing new. Although you guys, for some reason, don't use any mechanism arrows in Gen Chem or think about mechanism. But that arrow movement is shown on the previous page, right? Where we have a lone pair of the basic atom making bond to the hydrogen, and the bonding pair between the H and the Z. Here I showed it as Z. On the other page I showed it as A. It's two different, just generics. Both of them are commonly used. Electrons move on to Z, and so there's now a lone pair there. I didn't show a charge because it doesn't have to be a charge. If it's neutral, it's going to become minus, but if it's positive, it'll become neutral. You can determine formal charges, right? Okay, example acids. HCl, strong acid, pKa like about -7, somewhere in that range, strong acid. Of course, lower the pKa, stronger the acid, right? Acetic acid, which is an organic acid. It contains carbons, okay? Has a carboxylic acid with a methyl group. It's acetic acid. pKa is about 4. Carboxylic acid, pKa of about 4 to 5, okay? That's considered a weak acid. Thus, partial ionization if you put it in a protic solvent. Whereas strong acids, of course, completely ionize. We can get even weaker. We can go to maybe an alcohol. pKa of about 16, which is similar to water. At this point, we don't consider such an acid. okay? Although it can act as an acid. Water can act as an acid, but we don't call it an acid. Typically, you don't call compounds acids until their pKa gets below blood pH, which is what? About 7? Okay. If it's below 7, then you start calling things acids, like acetic acid with pKa of 4. Okay? Of course, if you look at the hydrogens on like an alkane, just a hydrocarbon, these hydrogens have pKa greater than 40. They're essentially non-acidic. We have to understand this trend of why. The trend here is based on 4 different things. They're shown here. Just like with our physical properties or our IMFs, we had 1 through 4. We also have 4 different ones here, and we will go through each of them individually. Number 1, electronegativity and size of A. When A is an atom, a single atom. So let's look at that. Water versus HF. Which one's more acidic? Well, hopefully you know HF. It's a hydrohalide hydroxylic acid, similar to HCl. Yeah, HF is more acidic. But why? Can you explain why? Okay, here's how we do it. First off, anytime you're looking at determining the strength of the acid, what you really need to look at is the conjugate base. You need to look at the conjugate base. And we need to ask, how stable are the conjugate bases? First off, these are the conjugate bases. Can you show the conjugate base for any acid? Yeah, I hope so. Should be able to do that, right? Conjugate base of water would be hydroxide. Conjugate base of HF would be F minus. Which one's more stable? Because here's the answer. Whichever one of these is most stable, that's the one that's going to be formed more readily. Now, how do we judge which is more stable? Well, 1A, we're looking at electronegativity. And the F minus is more stable because it is more electronegative. It's just a periodic trend. It's more able to handle the negative charge compared to the oxygen. That makes it more stable. Thus, HF is more willing to give up the proton and to act as an acid and to come here compared to water. Water is not as willing to act as an acid because where it's going is not as stable. So this is a electronegativity argument. Which is more acidic, water or ammonia? Well, what do we need to look at? We need to look at hydroxide, right? The conjugate basis. It's the conjugate base of ammonia. NH4 plus. No, the conjugate base, not the conjugate acid. It's the conjugate base of ammonia. Vlad? NH2 minus? Yes. How many lone pairs on the nitrogen? 2. Minus. You got to know how to show conjugate bases. You should already know that, guys. Right? You learned what a conjugate acid and conjugate base is at Gen Chem? Yeah? All right. Let's show it. Which one's more stable? O minus or N minus?
O minus.
Which one can handle the minus better?
Oh,
Oxygen. Why?
more electronegative.
We're under 1A. It's more electronegative. Okay, you know your periodic trends? Well, it's more electronegative. It likes minus better. It's able to handle it better. It's okay being minus. This is more stable. Thus, water is more willing to come here, act as an acid and give up the proton. Okay? So water is more acidic than ammonia. Which is more acidic, water or methane? Well, we're going to hydroxide, and this is going to CH3 minus. I mean, which one's more stable? O minus, right? More electronegative. It's way much more stable than that. Methane doesn't want to give up an H and become this high energy, low stability carbanion. Compared to oxygen, oxygen doesn't mind becoming O minus. Okay? Rarely do you want to make a C minus. It's very difficult. We will see C minus. That methane is not eager to become minus. Okay? Carbon is not that electronegative compared to oxygen. CH is rarely going to be acidic. Okay. Now 1b is size of the atom. Which is more acidic, HCl or HBr? Well, what do we need to consider? Conjugate base. What's conjugate base of HCl?
Zero minus.
Cl minus, right? What's conjugate base here? Which one's more stable? When you go by electronegativity, which one's more stable?
Zero.
Chlorine, because it's higher. Chlorine's more electronegative. Okay? But you would actually be wrong here. Because size of the atom actually trumps electronegativity. Size of the atom is more important, but only if you're in the same group. Okay? Which one's larger, Cl or Br minus? Okay? Br minus is larger. Periodic trend. Since it's larger, the minus is spread over a larger volume or nucleus. And if we can spread the minus out over the larger volume, that's a stabilizing factor. And thus this is more stable. Thus HBr is more willing to act as an acid and form this. Okay? Now most of this is said here. I'm not going to try to rewrite it here because I'm sure it's said right there. And I'm not going to read that to you. I'm just going to tell you, you can read it, read the version there. Okay? But remember, size trumps electronegativity, but only when you're in the same group. It can actually become a little bit like apples versus oranges if you start going diagonal. Okay? Which is more acidic, HBr or HI? HI, yeah, because I minus, which is what's going to form, is more stable than Br minus. Yeah, HI is your strongest of your hydrohalic acids. The I minus is so stable. That minus is spread over that huge iodine nucleus and particles. You can also make an argument about the number of protons in the iodine nucleus, which make up a stable atom. Essentially, the size is important going up the same groups. Okay, what's the most acidic hydrogen in this compound here? I got H's on carbons, nitrogens, oxygens, and sulfur. Which one is most acidic? Let's just take two. NH or OH, which is more acidic? OH, you'd rather have a minus on oxygen, right? It's more electronegative. OH is more acidic. Then let's say OH or SH,
SH.
which is more acidic? SH, why? Well, it's larger. And so we can arrive, that's your most acidic right there, the SH. What would be second most acidic? 2, then what? 3, what's the fourth? CH, you know, they vary because you got different CHs and we're not going to say, well, rank those. That's a little bit difficult, particularly that molecule. But there you go for the 1, 2, 3. The hydrogens on the heteroatoms. Yeah, SH compounds are more acidic than OH compounds, assuming the other structural features are similar. There are other things to consider here. For example, number 2, inductive effects. Look at these two compounds. This 2-carbon alcohol versus, well, this 2-carbon alcohol. This one has a fluorine on it. All right, which is more acidic? Well, first off, what do we need to consider? Conjugate bases. Here's the conjugate base of the first one. Here's the conjugate base of the second one. The minus is on oxygen in both, so we can't use an electronegativity argument. It's the same atom, right? What's the difference in the two? Obviously, this one has a fluorine. Okay? The charge is not on the fluorine, is it? The oxygen. Okay, here's a very important point. An sp3 carbon is typically known to be electron donating. That's the opposite of electronegativity. Okay? An electronegative atom is going to be doing this. I'm greedy, I like electrons. Give me your electrons. Okay? An sp3 carbon actually donates. Here. Oh, sorry. Here, take my electrons. I'm donating. Take my electrons. Okay? Now this is supposed to illustrate a single bond, which is a sigma bond. We can pull or we can push. This is called induction through single bond. You can inductively withdraw or you can inductively donate. An sp3 carbon inductively donates. Now, why? We could go on and sort of talk why and why. Hyperconjugation. It's not electronegative. It's just a classic statement of organic chemistry. So you got these sp3 carbons out here that are pushing towards the oxygen, donating. Out here we have the fluorine. The fluorine is electronegative. It pulls. Okay. Now it pulls to the single bond here, but that sort of pulls through here. It's like this, okay? You grab his hand or whatever, and I can pull, and by pulling through, see how he's pulling coming this way?
Yeah.
It doesn't have to be exactly connected. So I'm not showing it, but there's pull all the way through here because of the fluorine, okay? How do you stabilize a minus? Do you push electrons towards it, or do you want to pull electrons away?
Okay.
Everything wants to be neutral. Some things don't mind being minus, but ultimately neutral is best. You stabilize a minus by pulling electrons away. Okay? Which scenario are the electrons being pulled away? Here, by the electronegative atom. That's called withdrawing by induction through these single bonds. It stabilizes the minus and thus makes this one more readily or more willing to act as an acid than to come here. This one's more acidic because of an inductive effect. Oh, look at here. Methanol versus ethanol. Which one's more acidic? Well, of course, we're considering the O minuses, right? All right, I'm going to do this. You may do it differently on your paper, okay? Which one's more stable? Well, what's the difference? This one has an extra sp3 carbon. What does it do? Donates. Okay, which one's more stable? The first one. This one is essentially destabilized by induction of the extra carbon, inductive donation. Now there's not a huge difference in the acidity of these two, but in terms of predicting it, this one's more acidic. You don't stabilize a minus by pushing electrons towards it, you destabilize it. Which one's more acidic? Ethanol, or this is called T-butanol, 4 carbons, tertiary carbon. This chain of sp3 carbons donates. Here, because it's branched, each one of these is considered to be a donator. And that's like it's got 3 chains, and they're all pumping electrons into this carbon and into here. Where this one only has 1 chain. The branching acts as like different induction. Does that make sense? Okay. Now this could be like 10 carbons long, and it's really only considered 1 chain of induction coming towards this here. Where this is, branching is like 3. So which one's more acidic?
One chain.
Yeah, 1 chain, because the 3 chains pushing destabilizes the minus. If you destabilize the minus, this is not going to want to become minus as much. How about these two across here, the F and the chlorine? Which one's more acidic? Who says this one on the right?
Am I right?
Who says the one on the left? Yeah, left. Left wins. Why?
Because the fluorine's more electronegative than the chlorine, so it will pull more electrons away.
Yeah, we're looking at the O minus, right? Chlorine is more electronegative. I mean, this pulls also. Okay, chlorine pulls more. Question? Yes, thank you.
I thought you said the size mattered. You said the size matters.
Yeah, that's when the charge is on the atom. Is the charge on the chlorine? No, the charge is on the oxygen. Okay? Thanks for the question. I was anticipating the question. Chlorine is more electronegative. It pulls greater. Okay? The size thing, it probably says it up there. It's on the atom. As we said, the charge is spread over a larger volume. Okay, here, the charge is on oxygen, both of these. This guy is more acidic. How about down here, left or right?
What?
It is this. They're both pulling, okay? The statement we can make, though, is as the electronegative atom gets away, the effect does tail off. The effect does tail off. So it's not exactly like I can just tie a rope all the way through there and pull. If we had a rope, it wouldn't matter how long it was. Whatever's on the other end, I would still pull. But here, the effect tails off.
Will also implicate the carbons that push on the opposite side?
You want to try to make another argument. This actually has extra carbons. While it's pulling, they may be, yeah. That fits the answer. But the effect does tail off. Okay. There's some miscellaneous notes on the side there. What type of effects were those? Inductive effects. Through the single bonds, pushing and pulling. sp3 carbon is an inductive donator. Okay, another major effect is resonance effects. This is going to be more new to you because it's not based on things you know from Gen Chem as much. Okay, consider these two OH compounds. This is an alcohol, this is carboxylic acid. Obviously, this one's more acidic. It's called an acid. Okay? But why? Well, let's consider the conjugate bases. Conjugate base is this versus this, right? Which one's more stable? Well, obviously this one is. You know that's more stable because the one that's more acidic is going to have the more stable conjugate base. But why is it more stable? Well, it's resonance because we're under number 3. But what is resonance? First off, induction would give you the answer here. Because this just has these sp3 carbons donating. Where over here we can say, hey, we may have some donation by this sp3, but this oxygen is pulling this way, and it's kind of away from the other minus. It's not fully away, but it's certainly not towards it. And you say, well, there's a pi bond here. Yeah, there's also electronegativity in the sigma bond. But we can still call that sort of dipole induction. But we have resonance here. That's going to be the more major effect. Resonance tends to be a greater effect than induction. Let's look at this. First off, let's talk about hybridization. Hybridization of that oxygen. Anybody? How many regions around it? Electron regions? 4. Yeah, it's sp3. Okay, hybridization of this oxygen.
SP2.
sp2. Why? Because anytime a lone pair is next to a p orbital, it's going to want to be. Okay? This is that very important exception. So we have one LP and p orbital. By the way, let's look at this. The conjugate base has an extra lone pair. Okay? Both cases. Here, the lone pairs are all in sp3 orbitals. Here, one of them is in a p orbital. Why? What's it doing? It's interacting with adjacent p orbital. Right? That's why we said it would do that. Well, guess what? That's a very stabilizing effect. This guy is stabilized by resonance. This is resonance. P orbitals interacting. One way we can maybe say this very simplistically is the extra lone pair that this oxygen took on has something to do. It's able to interact with the neighboring p orbital by resonance. We can show resonance structures sort of like this. This is all just sort of an overview. Well, resonance structures. These pi electrons, we can move them up. So the oxygen is electronegative. We can get to a structure like this. Then these electrons we can move in, make pi bond here. And we're showing resonance structures, which are alternative flow structures of the same molecule. One thing this does is it spreads the charge out. In this structure, this oxygen has a minus, but in this structure, the oxygen is neutral. This is sort of an odd resonance structure. It's not as good because there's 3 charges. These are sort of your best resonance structures. The true structure is a blend of these. The true structure is a blend of these. Let's just blend these on the outside. If you blend them, here you have double bond between oxygen, here you have single bond. The average of that is like a bond and a half. And that's what I'm trying to show here. Okay? Between the carbon is a bond and a half. Over here we have a single and a double. The average of that is a bond and a half. Here we have a negative oxygen and a neutral oxygen. The blend of that is a partial minus, partial negative. And here we have a neutral and a minus, and the blend of that is partial minus. This is actually the true structure. It's called a resonance hybrid of these two sort of fake structures. And the important thing is, the oxygen does not have a full minus charge. It only has a partial minus charge. And a partial minus is going to be better than a full minus. On the other hand, this oxygen is sp3. Okay? One of these lone pairs is not in a p orbital. Since it's not in a p orbital, none of this discussion applies to this. And thus, this is an isolated anion. The oxygen is full minus. That oxygen here is not really full minus, is it? It's really what? It's actually only partial minus. Because of resonance, this is not a full description of the true structure. Resonance we'll have to build. Here's perhaps a take-home. If we can delocalize the charge by resonance, that's a stabilizing effect. If we can put a lone pair in a p orbital and give it something to do, i.e. bonding with the next carbon by pi bonding, that's a stabilizing effect. Recognizing that one of these lone pairs is in a p orbital is the first step. Recognizing that none of those are in a p orbital is also a major first step. Okay, we'll have to build on that. Please look ahead. There's lots of things in this handout. You really need to look ahead at this material. Have a good week, guys. Have a good week.